Great, thank you. This mic works, everyone in the back can hear me? Okay, cool. All right, so yeah, everyone, my name's Steven. I'm a NSF postdoc fellow here at Caltech. So I usually work in the realm of exoplanets, but I've recently branched out into the regime of brown dwarfs. And today I'm going to be telling you about how we can infer the origins of close-in brown dwarfs based off the stellar obliquity distribution. So if you don't sort of live in my little bubble of research, stellar obliquity might be a term that you're unfamiliar with, so let me just do a quick definition. When I say stellar obliquity, I'm referring to the angle between the stellar spin axis and the orbital axis of its companion. You can also think of this as the orbital tilt of the companion if you're in the reference frame of the star. So throughout this talk, I'm going to use a couple terms that I'll just define now. When I refer to in aligned or prograned orbit, I'm referring to something with a lambda of 0. So lambda is this angle. So something on the bottom here where the planet's sort of going around the star in the usual direction like they do in the solar system. When I refer to a misaligned or polar orbit, I'll usually be referring to orbits that have a lambda of 90. So this is when the companion actually orbits over the poles of the stars rather than just around the equator. And when I refer to something that has a retrograde orbit, referring to something that has a lambda of 180, so the orbit in this case goes in the opposite direction of the stellar spin. So these stellar obliquities are really informative because they give us a window into the origins of close-in planets and companions. So to demonstrate that here, I'm showing a scatter plot where on the y-axis we have the sky projected stellar obliquity, and on the x-axis we have the stellar effective temperature. And so again, on the bottom here we have the aligned and prograde orbits. In the middle, we have the polar orbits, and on the top, we have the retrograde orbits. And so each point here is a hot Jupiter system for which we have measured the stellar obliquity. And you'll probably notice, based on how I color the points here, that there's an immediate correlation here. Specifically, the cooler stars tend to have hot Jupiters that are on aligned orbits, and the hotter stars have a much higher probability of having these polar and retrograde orbits. But the separation is roughly at the craft break. And so the idea behind this is that the cooler stars have convective envelopes that can dissipate tides really effectively that are excited by the hot Jupiters. And the dissipation of these tides essentially causes a realignment of the stellar spin axis and the orbital axis. Whereas the hotter stars have radiative envelopes where we think that the tides are not dissipated as easily. And so essentially, these hotter stars retain the primordial obliquities of these systems over very long timescales. And this is really informative for hot Jupiters because we don't really know how hot Jupiters got so close to their stars. We don't think they can form there. They probably form farther out via these mechanisms that Ben talked about before. So probably core accretion or gravitational instability, and then migrated inward somehow. So the fact that these hot stars all have very misaligned obliquities suggests that these planets probably underwent very dynamically hot histories that caused them to move inward. So they probably moved in on a very inclined and highly eccentric orbit after some kind of scattering. So the question that I became interested in is, can you perform the same exercise for close-in brown dwarfs? So when I say brown dwarfs here, I'm referring to planets or objects with, not planets, maybe, objects with masses from 13 to 80 Jupiter masses. And essentially, I want to know, can we perform the same exact exercise? So look for the transiting brown dwarfs around hot stars, measure the obliquities, and then infer something about how they got to these close-in orbits. And similar to the hot Jupiters, we don't think brown dwarfs can form so close to their stars. They probably are forming very far away and then moving in somehow. Okay, so going back to this picture, I'm going to add all of the brown dwarfs for which we have these measurements for. So these are the yellow squares now. And you can see that there are only 4, so we don't have a lot. Preliminarily, you might say, well, they all look pretty aligned. We don't have any retrograde or polar orbits, but the sample size is still small. All right, so why don't we have more of these measurements for transiting brown dwarf systems? And there are essentially 2 reasons. The first is that these close-in brown dwarfs are really quite rare. We know this from early radial velocity surveys that have sort of quoted this region called the brown dwarf desert, where you have a lot of planets and you have a lot of stars, but you don't have a lot of brown dwarfs, less than about an AU from their stars. The second reason is that most transiting brown dwarfs prior to the TESS mission orbited stars that are really just too faint to get these measurements from the ground. But luckily, TESS has really changed all of this in the last couple of years. So now I'm going to show a quick animation of all the new transiting brown dwarf systems that have been discovered thanks to TESS. So I'm showing mass versus orbital period here. The size of each point indicates how bright it is, and then the color indicates the host type of the spectrals. the spectral type of the host star. So TESS comes into the picture around 2017 or 2018, and we sort of get this explosion of brown dwarfs. So in particular, we started to get a lot of brown dwarfs orbiting very bright stars, and specifically A and F type stars. So these are exactly the hot host type stars that we want to be probing to characterize the stellar obliquity distribution. So I got together with a couple colleagues, specifically Theron Carmichael, who's a postdoc at University of Hawaii, and Noah Bowell, who is a graduate student at Michigan State University. And we decided to put together a survey to start measuring the obliquities of these newly discovered brown dwarf systems. So we're calling this the Oatmeal Survey, which stands for the orbital architectures of transiting massive exoplanets and low mass stars. We couldn't find a way to get, thank you. I couldn't come up with a good acronym that has like a B and a D in it for brown dwarf consecutively. So this is what we went with. So yeah, our objective is essentially to really compile a more complete sample of stellar obliquities for these systems. And so specifically, we want to access the dynamical histories of these really close-in brown dwarfs. And I think that there are really three distinct mechanisms that can explain how these objects are getting to such close-in orbits. And luckily, they should all have distinct obliquity distributions. So all the lambda distributions for these three mechanisms should be different. So on the far left, we have something akin to disk migration, like a giant exoplanet might do. So essentially, your brown dwarf forms very far away, probably in the disk, maybe via disk fragmentation, exchanges angular momentum with the disk in a way that causes it to move inward. So this should result in pretty much low lambda systems, so mostly prograde and aligned orbits, assuming that your disk is primordially aligned with your star. The second mechanism is similar to how we think hot Jupiters got to their close-in orbits. So you have another massive body in the system that causes the orbit of your brown dwarf to become very eccentric and very inclined. And then when it gets eccentric enough, it can interact tidally with the host star in your periapterin. Tidal dissipation starts happening and the orbit shrinks and circularizes. So this should result in a pretty wide range of obliquities, but it has this like particular preference towards nearly polar orbits, it turns out. And the last option is some kind of ejection or capture from if you have a free-floating brown dwarf, you may have gravitational capture by a star. And so if this brown dwarf is captured on a highly eccentric orbit, you could again get tidal interactions shrinking and circularizing the orbit. And it turns out, so there are some new observations from WST that indicate that these free-floating brown dwarfs might actually be quite common in young stellar clusters. So this isn't unreasonable to think that this could happen. And this should pretty much result in a random distribution of stellar obliquities. You should have just as many retrograde orbits as you should polar orbits. Okay, so how do we actually measure these obliquities? And this is where Keck comes into play. So here I'm showing a diagram on the left of a companion transiting a rapidly rotating star. So the blue part of the star is blue shifted, red part is red shifted. And on the right, I'm showing the evolution of the stellar line profile as the transit occurs. And so you notice that there's a little bump in the line profile that is correlated with where in the stellar disk the object is transiting. And so to get these observations, you need two things. The first thing you need is a very high resolution spectrograph, because you need to actually resolve the stellar line profile. And the second thing you need is a really highly stable spectrograph. So ideally something that's fiber fed. And so to answer this question and to go after these brown dwarfs, we're really utilizing KPF to this really incredible stability that it has. Okay, so this is the method that we used, and so we can move on to our first detection. So this was a detection that we got with KPF almost exactly a year ago today of the transiting brown dwarf GPX1. So on the left, we're showing the KPF data. The y-axis is time, so going up, you're moving forward in time, and the y-axis is essentially the velocity space of the stellar line profile, where I've normalized by the out of transit line profile. And so the signature that you're looking for is this diagonal blue line here. This is that wiggle in the residuals. And essentially the direction that this line is moving is telling you what the stellar obliquity is. So if it's going in this direction, as we see it going, you have an aligned prograde orbit. If it were going up and down, you'd have a polar orbit. And if it were going in the opposite direction, you'd have a retrograde orbit. And so you can see that we measure a pretty nicely aligned prograde orbit here. It's pretty close to a lambda of 0, in fact. Okay, So where do we sit now with the current population? We have added one more point to this diagram. And there's actually a sixth one in here that's not that just recently was published, but I didn't get a chance to update. That's around over here. So also a line that was by one of Melania Rice's students at Yale. So again, we have another prograde aligned orbit. And so you might be tempted to say, maybe we're starting to see a trend here. Maybe all of the brown dwarfs actually do have these prograde aligned orbits, which is distinct from the hot Jupiters, which tend to have these very misaligned orbits, which is maybe telling us about how these close-in brown dwarfs formed. Maybe they formed in the disk via disk fragmentation or core accretion, and then migrated inward via accretion of the disk, rather than something like high eccentricity migration. But again, the sample size is still small. And so our collaboration is really, aiming to increase this by a factor of 3 or even 4 to get a good understanding of the underlying distribution. And so that's my talk. Leave up summary slide, and the QR code has the Oatmeal 1 paper that I just showed before, which was accepted just last week. So you can check it out there.